we have seen that every substance, whether an element, a solid solution or a compound, has got its characteristic X-ray diffraction pattern. Thus, X-ray diffraction pattern of a phase is very much characteristic of that phase alone. In a sense, an X-ray diffraction pattern of a substance or a phase is just like the fingerprint of a human being, just as by distinguishing between the fingerprints, two persons can be distinguished. In a similar manner, by distinguishing between the powder patterns or powder X-ray diffraction patterns of two substances or phases, the two phases can be distinguished. Now, let us suppose that we have got a phase mixture of A and B. Now, here we see a number of diffraction lines. The lines due to the phase A have been marked, and the lines due to phase B have also been marked in this powder pattern. Now, before going to the topic of quantitative phase analysis, I would like to say a few words about the quantitative elemental analysis that can be performed by the measurement of the lattice parameter of a phase or phases in a mixture. Say, for example, we have got a single phase solid solution of gold in copper. The lattice parameter value will depend on the concentration of gold in the alloy. As the amount of gold in the solid solution increases, we expect that the lattice parameter of the solid solution will also increase, since the gold atoms are larger than the copper atoms. Let us consider a series of copper gold alloys. Let us measure the lattice parameters and then plot these lattice parameter values against the corresponding gold content. This is shown on the right hand side of the figure. By measuring the lattice parameter of an unknown copper gold alloy, we can find out its gold content with the help of this plot. So in this plot, the lattice parameter of the solid solution has been plotted along the y-axis, and the weight percent gold has been plotted along the x-axis. So this dotted line passing through these points shows how the lattice parameter of the solid solution changes as the amount of gold in the solid solution changes. So if we have got an alloy, an unknown alloy, we can simply have to measure the lattice parameter. Once you do that, you put the lattice parameter value over here and find out the corresponding gold content of the alloy. So in this manner, you can find out from the lattice parameter the quantitative chemical analysis in case of a solid solution. There are three different methods available for quantitative phase analysis by X-ray diffraction. The first one is what is known as the single line method. The second one is known as the internal standard method, and the third one is known as the direct comparison method. Now, I will describe all the three methods for mixtures using an X-ray diffractometer. First of all, we'll deal with the single line method. Now, as we are all aware, in a diffractometer, the expression for intensity of an XID line is given by the equation 1. This is written on the board also. So, I is equal to I0 e to the power 4 divided by m square C4 lambda cube A by 32 pi r into 1 by v square into f square p into 1 plus cosine square 2 theta divided by sine square theta cosine theta into e to the power minus 2m by 2 mu. Now, we know that I is the total integrated intensity per unit length of a diffraction line in the XID pattern. I0 is the intensity of the incident beam of X-rays. E is the charge on an electron. M is the mass of an electron. C the velocity of light. Lambda the wavelength of the incident X radiation. R is the radius of the diffractometer circle. A is the cross-sectional area of the incident X-ray beam. V the volume of the unit cell of the single phase material. F is equal to crystal structure factor. P is the multiplicity factor. Theta is the Bragg angle. E to the power minus 2m is the temperature factor, which is a function of theta, and mu is the linear absorption coefficient. So this expression is valid for a pure phase, a line of the pure phase. When we have a phase mixture of, say, two phases, alpha and beta, then there will be slight change in the expression. For example, if we measure the intensity of the same line of a phase when it is in a pure form, that intensity will be much higher compared to when this phase is present only as a small fraction of a phase mixture. So, when we are dealing with a phase mixture, a line of a particular phase, the intensity of a line of a particular phase, the expression for that must be multiplied by W alpha, the weight fraction, or C alpha, the volume fraction of the particular phase. Say, for example, this I here, this is the intensity of a particular line in the pure phase. The moment this phase, say the alpha phase, is present in a mixture containing the two phases alpha and beta, then the intensity of that particular line in the phase mixture for alpha will be written by multiplying this expression by C alpha and changing the value of mu, the linear absorption coefficient of alpha, as mu m, because we must write down the linear absorption coefficient of the mixture. Now, in this expression, the whole term which shown by this yellow chalk is a constant for that particular line. Therefore, we can write it as a k, a constant, and this will be multiplied by C alpha by mu m. So, this is the general expression for the integrated intensity of a particular line in a pure phase, and when that phase is present as part of a mixture of two phases, then the intensity of the same line will be written as k, that particular term, to C alpha, which is the volume fraction of the alpha phase in the mixture, divided by, instead of mu, we write mu m, the linear absorption coefficient of the mixture. Now, we know that when we are dealing with a mixture containing two phases, alpha and beta, then the mass absorption coefficient of the mixture, mu m by rho m, can be written as W alpha into mu alpha by rho alpha plus W beta multiplied by mu beta by rho beta. So W alpha is the weight fraction of the alpha phase in the mixture. W beta is the weight fraction of the beta phase in the mixture. Mu alpha and mu beta are the linear absorption coefficients of the alpha and beta phases in the mixture. Rho alpha and rho beta are the densities of the alpha and the beta phase respectively. Now if we consider a unit volume of the phase mixture, then the weight of the mixture will be simply equal to rho n, the density of the mixture. So weight of alpha in the mixture will be equal to W alpha to rho n. Similarly, volume of alpha will be equal to W alpha rho n divided by the density of the alpha phase rho alpha, and we know that the volume can be simply written as C alpha, and volume of the beta phase will be W beta rho n by rho b, and this can be written simply as C beta, because you know the whole thing we are talking about is for unit volume of the phase mixture. Now multiplying equation 3 by rho m, this equation 3 by rho m, we get mu n equal to W alpha rho m by rho alpha into mu alpha plus W beta to rho m by rho beta into mu beta, and this can be written as C alpha mu alpha, and this can be written as C beta mu beta. Since C alpha plus C beta, that means the volume fraction of alpha plus volume fraction of beta in the mixture is equal to 1, then this can be written as C alpha mu alpha plus 1 minus C alpha into mu beta equal to C alpha into mu alpha minus mu beta plus mu beta. Now if we put this value of mu m in equation 2 over here, we get I alpha equal to K C alpha divided by C alpha into mu alpha minus mu beta plus mu beta. This is our equation 4. Now when we consider the volumes of the two phases alpha and beta in a unit mass of the phase mixture, these are W alpha by rho alpha and W beta by rho beta respectively. Therefore now we can write C alpha will be equal to W alpha by rho alpha divided by W alpha by rho alpha plus W beta by rho beta, our equation number 5. Since W alpha plus W beta equal to 1, this equation can be written as W alpha by rho alpha divided by W alpha into 1 by rho alpha minus 1 by rho beta plus 1 by rho beta. Now if we combine the equation 4 over here, if we combine equation 4 and equation 6 over here and simplify, we can write down I alpha equal to K W alpha divided by rho alpha into W alpha into mu alpha by rho alpha minus mu beta by rho beta plus mu beta by rho beta. For a sample of the alpha phase in a pure form, if we get a sample of the alpha phase in a pure form, then all the terms for the beta phase in this equation will simply vanish, and therefore for the pure phase I can write down I alpha p for the pure form will be simply equal to K divided by mu alpha. Now if we divide equation 7 by equation 8, we can write down I alpha divided by I alpha p will be equal to W alpha into mu alpha by rho alpha divided by W alpha will be mu alpha by rho alpha minus mu beta by rho beta plus mu beta by rho beta. So what we can see here, that if we get a phase mixture of alpha and beta, and if we concentrate on a particular line of alpha in the diffraction pattern for the phase mixture, and if at the same time we look at the intensity of the same line in a pure form of alpha, then divide those two intensities, the first one by the second one, we get an expression like this. And here, if we know the values of mu alpha and mu beta, which are the linear absorption coefficients of the alpha and beta phases, and rho alpha and rho beta, the densities of the alpha and beta phases, then simply from the ratio of a line of alpha phase in the mixture and the same line of the alpha phase in a pure form, from this ratio, knowing the values of mu alpha, mu beta, rho beta, it is possible to find out the value of W alpha, the weight fraction of alpha in the mixture. And once you know the weight fraction of alpha in the mixture, and if the mixture contains only the two phases alpha and beta, the weight fraction of beta can also be found out. Now this method is known as the single line method, because here we compare the intensity of a particular line of the alpha phase in the mixture with the intensity of the same line of the alpha phase in a pure form. So from this single line method, knowing the values of the linear absorption coefficients and densities of the constituent phases, it is possible to find out the weight fraction of the two phases alpha and beta. Quantitative phase analysis by X-ray diffraction, namely the internal standard method. Say for example, we have got a mixture of three phases A, B and C. Let us suppose that we want to find out the volume fraction or the weight fraction of A in the phase mixture. So in the internal standard method, what we do is we mix a known amount of a standard phase for which all the parameters are known and mix it with the given sample and make a composite sample. Say for example, when we make the composite sample, say Ca is the volume fraction of the phase A in the original mixture, and suppose Ca prime is the volume fraction of A in the composite sample, and Cs is the volume fraction of the standard substance in the composite sample. Then what we do? Then we take an X-ray diffraction pattern of the composite sample in a diffractometer. So now for the composite sample, using the expression for equation 2, we can write Ia, the intensity of a particular line for the phase A in the composite sample, is equal to K1 Ca prime by mu m, where mu m is the linear absorption coefficient of the mixture, the whole of the composite sample. Now simultaneously, if we concentrate on a particular line of the standard, the diffraction pattern of which will also appear in the same XRD pattern for all the other components A, B and C, then Is can be written as a constant K2 into Cs divided by mu m. Now if we divide equation 10 by 11, we can write down Ia by Is is equal to K1 Ca prime divided by K2 Cs. Now, we have already seen in equation 5 how to find out the volume fraction of a phase in a two-phase mixture. This is the expression for equation 5. Now, extending this expression to the components of the composite which we have made up of A, B, C and S, we can write down Ca prime will be equal to W A prime by rho A divided by W A prime by rho A plus W B prime by rho B plus W C prime by rho C plus W S by rho S. This is our equation 13. In a similar manner, we can find out the expression for Cs also, which is equal to Ws by rho S divided by the whole thing over here. So, this is our equation number 14. Now, if we divide 13 by 14, we can write down Ca prime divided by Cs will be equal to Wa prime by rho A divided by Ws by rho S. This is our equation 15. Now, if we substitute in equation 12, this is our equation 12. Now, if we substitute in equation 12, we can write down Ia by Is is equal to K1 by K2 multiplied by Wa prime by rho A divided by Ws by rho S. This is our equation 16. Now, here K1, K2, rho S, rho A are all constants. Now, if while making the composite by adding the standard material, if the weight fraction is kept constant intentionally, then equation 16 can be written as Ia by Is is equal to K3 Wa prime. K3 is a new constant incorporating the various parameters. Now, the weight fraction of A in the original and the composite samples are related in this manner. Wa prime is equal to Wa into 1 minus Ws. Now, if we combine the expressions 17 and 18, we can write down Ia by Is is equal to K4, which is the new constant, into Wa. So, you see that if we concentrate on a particular line of A and a particular line of the standard material in the composite that we have made, and if we divide the intensity of A by the intensity of S, then this expression will be a linear function of Wa, the weight fraction of A in the phase mixture. So, this gives us a method by which we can find out the weight fraction of the different phases A, B and C in a phase mixture of A, B, C. Now, I come to the third method of quantitative phase analysis using X-ray diffraction. This is known as the direct comparison method. You see, in the first two methods, there are certain problems. For example, in the single line method, it is essential to have a pure material. One of the phases must be available in a pure form in order that the fraction of that phase in the phase mixture can be determined, and sometimes it may be very difficult to get a phase in a pure form. And in the second method, the internal standard method also, there may be a problem in getting a suitable standard. So, in this method, we really do not need to have the phases to be present in pure form, to be compared with, or some internal standard to be found out for making a composite. So, in this method, say for example, if we take a practical example, in hardened steels very often we find that there are two phases. So, a hardened steel is a mixture of two phases, namely FCC austenite phase gamma and BCT martensite phase alpha. Although martensite is body centered tetragonal, the tetragonality, if it is not that high, it can be considered simply as BCC alpha. So, we have a phase mixture of FCC austenite and BCC martensite. Now, what we do in this method, we choose two lines, one from each phase. So, we consider a particular XRD line from the austenite phase and a particular XRD line from the martensite phase in the X-ray diffraction pattern of the mixture, and then compare the intensities of those two lines. And as I will show readily, that a comparison of the intensities of the two chosen lines from the two phases, it is possible to find out the volume fraction of individual phases. Now, from equation 1, what we do, if you remember the equation 1, we put k, a constant, equal to I0 e to the power 4 by m square C4 to lambda cube A by 32 pi r. Now, this expression is the same for all the diffraction lines in the pattern. So, this is the same for all the diffraction lines in the pattern. We put it k. K is a constant for all the lines in the diffraction pattern. And then the remaining part, for example, 1 by v square f square p to 1 plus cosine square 2 theta by sine square theta cosine theta e to the minus 2m, we write as r. So, what is there in this expression, as we remember? V is the volume of the unit cell, F is the crystal structure factor, P is the multiplicity factor. This expression here is the Lorentz polarization factor, and this is the temperature factor. And naturally, the value of R for the two chosen lines will be different, although the value of K for the two chosen lines will be the same. So, in that case, we can write down the expression for I equal to integrated intensity of a line is equal to K R by 2 mu. The mu is the linear absorption coefficient of a material. As we know, this was our equation 1. So, this equation 1 can be written down in this simpler form by putting K is equal to this much, R is equal to this much. But when we are talking about a mixture, we have to make some changes. For example, this is valid for a pure phase, a line of a pure phase. But when we have a phase mixture, say when we talk about the gamma phase, then the intensity of a line in the gamma phase, there I have to put K instead of R, it will be R gamma, R gamma for that line, multiplied by C gamma, the volume fraction of gamma in the mixture. If the whole thing is gamma, then the intensity of a line, a particular line, will be very high. But if it is present only as a fraction, then intensity will automatically come down. So, intensity of the chosen line in the gamma phase can be written as K R gamma multiplied by C gamma. C gamma is the volume fraction of the gamma phase in the mixture, and instead of writing mu, the linear absorption coefficient for a pure phase, now you have to write down twice mu m for the mixture. Similarly, for the alpha phase, you can write down I alpha is equal to K R alpha C alpha. C alpha is the volume fraction of the alpha phase in the mixture by 2 mu m. Now, if we divide 23 by 24, we can write down I gamma by I alpha is equal to R gamma C gamma divided by R alpha C alpha. Again, you know that if it is a two-phase mixture of austenite and martensite only, then C gamma plus C alpha equal to 1. Now, if we solve these two equations, then it is possible to determine the value of C gamma and C alpha. But in order to do that, we have to find out the values of R gamma and R alpha. Okay. So, once we can determine the values of R gamma and R alpha, then by solving equations 25 and 26, it is possible to find out the volume fractions of the austenite and the martensite phase in the phase mixture of austenite and martensite in hardened steel. Now, if there are more than two phases, so say for example, sometimes there are three phases present in the hardened steel, namely austenite, martensite and some carbides. There we can write down the volume fraction of austenite plus volume fraction of martensite plus volume fraction of carbides equal to 1, and following the same method as we have done for a two-phase mixture, it is possible to find out the volume fractions of all the three phases individually. The direct comparison method is unique in the sense it neither needs the availability of any of the phases in a pure form, nor it is necessary to mix a standard material with the phase mixture in order to determine the volume fractions of the individual phases in the mixture. So, in that way it has got an advantage over the previous two methods. Now, for hardened steel, it is sometimes very essential to find out the volume fraction of austenite, because what happens if we make any tool out of that material, that during service the amount of austenite gradually changes into martensite or some other phase, and that may give rise to lot of internal stresses and dimensional instability. That is the reason why it is very much essential to find out the volume fraction of the retained austenite phase. Now, this can be done by using the microscopic method also. In fact, the microscopic method is pretty good and rather accurate for an austenite content about say 15% and above. But when it is below 15%, in that case the X-ray diffraction method using the direct comparison method can be a better proposition. So, this is the reason why the direct comparison method is very useful in industrial practice. Now, I will illustrate the use of the direct comparison method taking a practical example. Let us consider a high carbon steel sample. Now, if this sample is taken to the austenitic range and then directly quenched in a bucket of water, we are going to get two phases, martensite and some austenite. Now, if we take the X-ray diffraction pattern of the sample, then the pattern will show lines of both austenite and martensite. Now, this is a schematic of the line positions in the X-ray diffraction pattern for the austenitic phase and also for the martensitic phase. So, in the direct comparison method, if we want to find out say the volume fraction or the weight fraction of austenite in the hardened steel, we have to compare the intensities of one line from each phase. For example, in this particular case, we choose the 200 line of martensite and 220 line of the austenite. Now 200 line for martensite, we can see that the 2 theta is 75.84 degrees, and for 220 line of austenite, the 2 theta is 90.06 degrees. What happens essentially is, when we talk about martensite, the lines 101 and 110, they should be shown as separate lines very close to each other. Similarly, 002, 200, these two lines should be seen very close to each other, and 112, 211 and 202, 220, these are to be shown very close to each other. But you see, the resolving power should be very high in order to see these as very distinct lines, but it is normally not possible. Moreover, the reason for this is because of the presence of micro strain, and also because of the fineness of the grains, the lines show some broadening. As a result, these two doublets, so to say, lines will appear as one, these two will appear as one, these two will appear as one, these two will appear as one. So, if we take a practical example and draw the intensity versus 2 theta plot for a composite of martensite and austenite phases, we see that this is, say, the 200 alpha peak, this is the 220 gamma peak, this is the 211 alpha, this is the 311 gamma, this is the 220 alpha, etc., etc. Now, as we know, the background varies from 2 theta 0 to 2 theta 180 degree, and the background goes up as 2 theta increases. Say this is the background radiation here. Now we are going to use the direct comparison method in order to determine the values of the volume fractions or the weight fractions of austenite and martensite in the hardened sample. As we have seen already, if we choose a particular line of gamma and a particular line of alpha, we can write down I gamma by I alpha is equal to R gamma C gamma divided by R alpha C alpha. So, I gamma and I alpha, these are the integrated intensities of the chosen gamma and the alpha lines. Now, if we want to find out C gamma, we need to calculate the values of I gamma, I alpha from the pattern, and also R gamma and R alpha. Now, if we put a transparent graph paper on top of the I versus 2 theta plot as we obtain from a diffractometer, we find that the area, the integrated intensity, which is proportional to the area under the line. So, here for the 200 alpha, there are 191 small squares of the graph paper within this region, and if we compare it with the 220 gamma peak, the number of small squares is 44. Therefore, we can write down I gamma by I alpha is equal to 44 by 191, which is equal to 0.23. So, this much can be calculated from the plot of I versus 2 theta straight away. Now, we have to find out the values of R gamma and R alpha with the help of the following equation, as we have already seen. So, this is the equation for R. Now, how to determine these values? In order to do that, we need to have a number of tables showing the values of different parameters. For example, for measuring the value of V, the volume of the unit cell in the two phases, we need to have the lattice parameter data. Say for example, for BCC alpha, this is the lattice parameter 2.866, and for FCC gamma, this is the lattice parameter 3.571. Now, we need to have the crystal structure factor data. So, for BCC, we know that F square is equal to 4 small f square. Small f is atomic scattering factor, and when this is possible when H plus K plus L is an even quantity, and it will be 0 when H plus K plus L is an odd quantity. On the other hand, for FCC Bravais lattice, value of f square will be 16 small f square, where f again is atomic scattering factor, and this is true for HKL unmixed, and it is equal to 0 when HKL are mixed. Then you get another table for multiplicity factors. So, on this side are shown the HKLs, and on this side the value of the multiplicity factor. So, if the plane is HKL, that means HKL all three are different, then multiplicity factor is 48. HHL multiplicity factor is 24. 0KL type of planes multiplicity factor is 24. 0KK type of planes multiplicity factor is 12. HHH type of planes it is 8. For example, for 111 planes multiplicity factor is 8. 00L planes it is 6. So, 100 plane it is 6, etc., etc. So, using these tables we can calculate the value of f square, we can calculate the value of p, we can calculate the value of v, etc., etc. Then comes the Lorentz polarization factor, 1 plus cosine square 2 theta by sine square theta cosine theta. Here I have plotted only some definite values relevant to our problem. So, here it is theta in degrees from 40 to 46, then it is 0.1, 0.2, 0.2, 0.3, 0.4, etc., etc., 0.9. For example, if theta is 40 degrees, then this is the value of the Lorentz polarization factor. If on the other hand theta is 40.1 degree, then the Lorentz polarization factor is this. If it is a 42.5 degrees of theta, then you have to find it out. So, it will be 2.994. If it is say 45.9 degrees theta, so it is 2.789, etc., etc. So, from this table we can find out the value of the necessary Lorentz polarization factor for the lines. We are using say a cobalt K alpha radiation in this particular case, and the wavelength is 1.7901 angstrom. Now, the value of sine theta by lambda is given here. This is theta. So, we find out the value of sine theta in each case divided by the lambda that is used. So, these are the values of sine theta by lambda, and here the temperature factor has been given as a function of sine theta by lambda, and naturally for any line we calculate first the sine theta for lambda, and corresponding value of sine theta by lambda you can find out what should be the value of the temperature factor. So, using all these different tables we can find out the value of R for the chosen lines from the Martensite and the Austenite phases. Now, if we look at the Austenite phase, we can write down A is 3.571 angstrom. So, V, the volume of the unit cell, is 45.54, 1 by V square is 0.0005, f square is 16 small f square, small f is the atomic scattering factor, p is equal to 12. Now 2 theta for that Austenite line which we chose is 90.06, so that theta is 45.03 degree, and using the table I shown earlier, the Lorentz polarization factor is 2.828, sin theta by lambda for that particular line is this equal to 0.40. Corresponding to that, we can find out what is the temperature factor, which is 0.89. So if we substitute the above values in the equation 21, what we find, R gamma is equal to 0.0005 into 16 f square into 12 into 2.828 into 0.89. So this is true for the 220 gamma line. In a similar method, when you look at the chosen line from the martensitic sample, which is the 200 martensite line, A is 2.866 angstrom from the table which I have shown already. So this is the value of volume V, units of the unit cell 23.54, 1 by V square is 0.0018, capital F square is 4f square. This F stands for the atomic scattering factor. For this type of plane, multiplicity factor is 6 from the table, and for this line 2 theta is 75.84 degree, so theta is this much, and the value of the Lorentz polarization factor can be read out from the table as 3.561. Sin theta by lambda can be calculated to be 0.34, and using all those values, and the temperature factor comes out to be 0.92. Now we can substitute the above values in equation 21 and get R alpha is equal to 0.0018 into 4f square into 6 into 3.561 into 0.92. So now we have found out the values of R gamma and R alpha for the chosen lines. So putting those values in this equation, we have already seen I gamma by I alpha is 44 by 191, that is by direct measurement on the I versus 2 theta plot, and then put the values of R gamma and R alpha, and here multiplied by C gamma and C alpha. So 0.23 is equal to 0.242 C gamma by 0.142 C alpha. So C gamma by C alpha is 0.135, but since the material contains only two phases, gamma and alpha, we can write C gamma plus C alpha is equal to 1. So you see that now we have got two important expressions, one for C gamma by C alpha and the other for C gamma plus C alpha. Now if we solve these two equations, we find the value of C gamma is 0.12. That means the volume fraction of austenite phase in the hardened steel is 12%. So this is really a very elegant method of determining the volume of volume fraction, the value of the volume fraction of the austenite phase in a sample of hardened steel. Of course, this method can be extended in other systems also. You see, till now I talked about the diffractometer method. Sometimes in some laboratories people use the old Debye-Scherrer method too in order to find out the volume fraction, the quantitative measurement of the volume fractions of different phases in a phase mixture. So in that case, how we determine the integrated intensity? Now the photographic density of an XRD line on a film like this can be measured using a microphotometer. So in its simplest form, In its simplest form, a microphotometer consists of a light source which allows a narrow beam of light to be transmitted through an X-ray film and strike a photocell connected to a galvanometer. So, we have the X-ray film, say these are the X-ray lines, and naturally these are much darker as compared to the background, and we have a light source which can illuminate the X-ray film from below. Above there is a photocell which will record the transmitted light intensity, and this is again connected to a galvanometer. The galvanometer deflection will be proportional to the intensity of the transmitted light, we say I. Now, in this figure, several XRD lines have been shown on a film, and the background, as you can see, changes from light to very dark as we move from 2 theta is equal to 0 to 2 theta is equal to 180 degree. Now, this is the figure B, and here the point X corresponds to where the galvanometer shows 0 deflection, and Y is the point where the galvanometer shows maximum deflection. Now, for the lines 1, 2, 3 and 4, this is what we find the galvanometer deflection. This is what we get for the 4 lines according to their intensities, and the photographic density or the blackening of a line is given by the relation d is equal to d is equal to log I0 by I to the power 10 at the base to the base 10. I am sorry, d is equal to log I0 by I to the base 10. I0 is the intensity of the, not the X-ray beam, it is wrong here. I0 is the intensity of the light incident on a film, and I is the intensity of the transmitted beam. So, you see that if we have a photographic film which records the diffracted intensity from a phase mixture, then this is how we can find out the area under the curve and measure the integrated intensity and use the same method as I have described already.